afternoon, students. Welcome to one other lecture in the Advanced Green Manufacturing Systems. So, continuing on with the simple heuristics and why heuristics are used, because they can start with one variable, taking a solution without losing the feasibility, and once all the variables are taken care of, then that final solution which is feasible, then most of the algorithms stop. So, let us look at this an example, the previous case example. Okay, this example is taken from the Lieb R. Soule textbook, okay, titled Industrial Scheduling. Okay, and this I am using this example to just demonstrate this particular case. So, so let us say there is a heuristic. So, in this case there is two things, one is the processing time and there is a due date. So, heuristic 1, okay, the first heuristic we think about, from the list of the job, from the job list, find the job with lowest processing time and schedule it first. Okay. Then repeat until all jobs are done. Okay. So, what we are doing is, let us say we have 4 sequence positions. So, let us call this a sequence position 1, 2, 3, 4, and here is the drilling machine. So, 1 means it is close to the first one that is going to the drilling machine, right. So, we go to the job and find out the processing time, which is the one with the lowest processing time, that is 3. So, it goes in this sequence position, right. Then this is over. So, we do not consider this anymore, okay, done. Now, let us cut this one now. The next one is we go through this list and we find which is the next lowest one, which is 27. So, what we put here is 2, okay, this is done. Then we go through the list, we find that the next lowest processing time is 4, 28. So, this goes here, and then we find out the last one is this one. So, this goes into 1. Okay. So, 3, 2, 4, 1 is the now we are done with all the jobs and now we have a sequence. Okay. So, we iteratively built a sequence in this direction. So, take decision on sequence position one at a time. Okay. So, each sequence position one after another we take, then we move to this, then we move to this, and we move to this. Okay. So, this type of a heuristic, what we just did is, wherever we find out the lowest or shortest processing time or shortest, okay, this process is called as SPT, shortest processing time. Okay. This is also sometimes known as a single pass heuristics, because in one pass you are able to get a solution. Okay. Another example of this is what we call as heuristic 2. You can call it as from job list, find the job that has the earliest due date. Assign to the first sequence position. Continue till all jobs are done. Okay. So, how will we do that? If you think about it, we say again have the 4 sequence positions 1, 2, 3, 4, okay, and here is your drilling machine. Okay. So, now we go through the due dates. The due date, the job with the earliest due date in this case is 1. So, you take that one and assign job 3 right here. Okay. Then the next one that we think about it is 36. So, that is job 2. Okay. This is then job 4, and then we get to job 1. Okay. So, in this particular case you can see that the sequence of this heuristic is called as earliest due date. Okay. So that's another example. The third way you can do is you can calculate something called as a slack. Okay, slack means what is the difference between. So the slack of this job is this is okay the due date minus processing time 49 minus 37, that is the one slack. This is 36 minus 27. Then this is 1 minus 1, that's equal to 0. Then 37 minus 28. So in this case is 28 plus 38, so it's 9. Then this 1 minus 1 is 0. This is also 9. Then that is 12. Okay. So what we do is then find out so first we calculate the slack and then take the job with the least amount of slack and then assign to the sequence position. So then you can get in probably get a different sequence in this regard. Okay. So those kind of ways you can do this. So if you think about this approach, then your sequence position will be 1, 2, 3, 4 sequence positions. The first one you assign is job 3. Second one, let's say we picked up job 4 in this regard, okay, because this is the least slack. So we picked job 4. Then we picked this guy, so that's job 2, and then there is job 1. Okay, so this gives you a different sequence. This is called a L slack approach heuristic or least slack heuristic. Okay. So there are many approaches that you can use to solve this problem, and each one of them will give you one different solution. So what you do is once you find the solution, calculate the objective function value. So decide good. Okay. Sometimes what people do is they take different heuristics like this 3-4 different heuristics, and then from there they decide which result is better compared to other kind of cases. So this is what we call as a heuristic, where these solutions, all these solutions, okay, these solution and these solutions, the solutions are not provably optimal. Okay. We cannot really prove that the solutions are optimal. That is the most important part of such an approach in this regard. Okay. Now from here we move to, so we already talked about the heuristic approach. Now we get into what we call a Stebbu and simulated annealing method. I'm not going to get into examples in this case, but I am just going to familiarize with you because there is another presentation by Dr. Amandeep Singh in this regard, which will help you to understand this process better. So now we discuss meta heuristics. Okay. So heuristics is something like where you start taking one decision variable and then you incrementally keep on doing it until you get all without violating the feasibility, and once you get the feasible solution you call it good. So then we talk about something called meta heuristics. They are algorithms that apply one of several high level strategies to obtain a better diversified search, to obtain a better and diversified search, better solution. So what these algorithms, the meta heuristics, the difference between the normal heuristic and meta heuristics is that they have a complicated high level strategy to get better and diversified solutions for these kind of problems. Okay. So both Stebbu search and simulated annealing SA works by selecting moves at each iteration, where the movement is from one solution to another. Okay. The idea here is that you select a move for each iteration where the movement is from one solution to another. So like for example, if you think about the previous case, you have 4 sequence positions. Okay, if you look into this, one is 1 4 2 3. So we say 1 4 2 3, and now we want to find out what. Now the way to do it is we say we exchange these positions. So we move to a next solution called 1 4 3 2, and see whether this solution is, this is the new solution. Okay, this is called movement. Okay, so you move from this particular solution. Okay, this is the old solution. So you move from one solution to another. You are not really changing one thing. You are basically actually moving from one solution to another, right? And until you find out which is the best possible solution. Okay, so the taboo search, on the other hand, what is it? What does taboo search do? Deals with cycling that will prevent those moves which will bring back to the earlier optimum. Okay, so what we do is we try to, this algorithm prevents the cycling. So taboo moves are something that you are not supposed to take, ideally speaking. So if I draw a graph, let's say the solution space of this problem is something like this. Okay, and let's say you started from here and you built a solution. Okay, so you move from one solution to another, you keep on moving until you reach this particular point. Okay, so this says, okay, fine, this is a one good solution. Okay, the parlance for this good solution is called as local optimum. We call this as a local optimum. Okay, so from here what happens is, there is no other way in any of this area. Even if you start from here, you will go back to this optimum only. So what is the way to get out of this optimum and reach this particular one? Let us say this is the global optimum. How do you do that? The one way to do is allow it to reach, take these moves. Okay, allow taking non-improving. Okay, non-improving, this is called as a taboo. Okay, by taking this move you are actually deteriorating the solution, right? The comparison is, if new solution better old solution, is a new solution better than the old solution? That is what we are actually comparing in a meta heuristic. And yes, then you take this. But in a taboo move, you allow them to take these moves which does not allow this to satisfy. So that is called as a taboo search. Okay, and simulated annealing on the same way is also of the same type. Okay, so the simulated annealing is that, okay, allow taking non-improving moves, you allow the algorithm to take non-improving moves according to probabilities, tested with computer generated random numbers. So what happens in taboo search is that you say, okay, fine, you do one thing, you allow the program. So in this case, for an example, let's say you are here, you are here at this point, and the you say the taboo list is, let's say, 20 non-improving moves. So what happens is, it will probably move from here 1 2 3 like this, and then within, so it will allow the system to take 20 non-improving moves, and within this, if you find that there is one move that is improving like this, then you will keep on climbing this until you reach this. So, the idea of this taboo list is to escape local optimum, okay, escape local optimum. Okay. Same way, the by using probabilities, you are trying to escape out of the local optimum and move towards a different solution. So, that is the idea, right. So, similar to annealing a taboo search, the only difference is that here there is a list, here there is a set of probabilities generated using random numbers, right. And we come to the last set or the last aspect of it is, which is of the meta heuristics, is what we call as the genetic algorithm. Okay. So, mostly people call this as evolutionary meta heuristics, meta heuristics. Okay. So, why is it called evolutionary meta heuristics? Okay. Here is what we are doing is we move beyond uh, any sequence of single solution. So, you move outside this single solution approach that we already mentioned, okay, to evolve a population. So, you are not moving from one solution to another, but what you are trying to do is you are trying to evolve a population, okay, of possibilities, or you are trying to find a population of options, okay, or you can think these possibilities are options, okay, um, improved over time by mechanisms that are similar to biological process. So, what you do here is, instead of moving from one solution to another, you develop mechanisms that allows you to create a pool of solutions, okay, and from the pool of solution, which is what you call as a population, then you find the best, one of the best possible options that you can get, okay. So, what you do is, so genetic algorithms, they evolve good heuristic optimum, okay, by operations of combining members of an improving population of solutions. So, this seems like a tough word, but I will try to make it easy. What you do is you use an operation of combining solutions. So, let us take a simple example what we said in the previous case. There are 4 sequence positions for us, okay, 4, 3, 2 and 1. So, let us look at the least slack and this one. So, it is 3, 2, 1, 4, 1. So, one solution is 3, 2, 4, 1, okay, and the other solution is 1, 2, 4, 3, okay, 1, 2, 4, 3, okay. So, let us say we have 3 solutions. So, this is your solution 1 and this is your solution 2, okay. For the time being, assume that these are good solutions, okay. Let us assume these are 2 good solutions. So, one way of doing the solution is that, okay, you can create a scenario of doing this. So, we want to take this job which is at the 4th sequence position. Let us take a cut here, okay. This guy is 4, okay. We want to change this, okay, and what we do is we take. So, in this case I want to try this 2nd sequence position, or let us try to find a place where we are trying to do this. So, if I move 4 here, so if I get a solution 1, 4, 4, 3, then this is not feasible, because what happens is this has gone away. So, one option we can do is you can do it as 1, 4, you move it here and then put 3, 2, okay. So, this guy comes this way, and this case I will have 1, 2, 2, 3. So, that is an unfeasible solution. So, you can do this 1, 2, 3 and 4, okay. So, these 2 solutions were derived out of these solutions, okay. So, you can think about it's actually not the case, because you require a little bit more of a complicated solution to do this. This is not really a good example what I gave, but the idea is that you remove. Okay. So, what the idea is that this is something called combine a pair of, okay, parent solutions to generate good uh, child solutions by breaking the parents at some point and combining them. So, what you are actually doing is you are cutting the parent in some places and then you combine them in a particular fashion. So, what we have done is we cut this solution out, this sequence position out, move them here and put the next one in that position. So, that kind of a thing, right. So, assume that because if this is a good parent, so we can say good parent, okay, good parent. So, from both good parents you should be able to get good children, that is the idea. Okay. And so, creating a scenario of like this for evolving the which mimics the biological evolution is what we call as a genetic algorithm. It is actually a very simple crude explanation for you guys to understand, because there is a ABC explanation that is coming from Amandeep in a much better fashion. So, it would probably help you to understand that better. So, thank you very much for your patient listening, and we will see you in the concluding lecture. Thank you.